All right, today we're going to demystify a concept you actually experience every single day, anytime you're moving: acceleration. We're going to break down what's really going on from a physics point of view. So let's just dive right in. I want you to think about this for a second. You know that feeling when you're in a car and it suddenly speeds up and you get pushed back into your seat? Or when a train takes off from the station? That feeling? Well, that is acceleration. It's the physical sensation you get when your velocity changes. And that change is exactly what we're going to pick apart today. Okay, so here's the official physics breakdown. Average acceleration is just the rate at which velocity changes. That's it. And this formula right here, this is our best friend for figuring it out. All it says is that acceleration, that's A with the bar over it, is just the change in velocity, which we get by taking the final velocity and subtracting the initial velocity, and then we just divide all that by how long it took for that change to happen. So what about the units? You're going to see this a lot: meters per second squared, or ms squared. And I know that can sound a little weird, a little abstract, but here's the cool part. It literally just means meters per second per second. So think about it this way. It's telling you how many meters per second your velocity is changing for every single second that goes by. It's not so scary when you break it down like that, right? Okay, enough with the theory. Theory's great, but let's see how this thing actually works in the real world. For our first application, we've got a racehorse, and it's just exploding out of the starting gate. Let's just walk through this one step by step, nice and easy. First up, step one. What do we know? Well, the horse starts from rest, so its initial velocity, v0, is 0. Easy enough. It hits a final velocity of 15 meters per second, but notice it's west. In physics, we need to define our directions, so let's call west the negative direction. That makes our final velocity, vf, negative 15.0 meters per second. And all this happens in just 1.80 seconds. Okay, now we just plug those numbers into our formula. We get negative 15.0 divided by 1.80, and that gives us an acceleration of negative 8.33 meters per second squared. Now don't let that negative sign throw you off. All it's telling us is the direction. The acceleration is pointing west, the same direction the horse is running. Makes sense, right? You know, that last problem brings up something that trips up so many people. They see a negative acceleration and they instantly think, oh, it's slowing down. But is that always true? The answer is nope, not necessarily. So let's clear this whole thing up right now. Okay, so this is the absolute key difference you have to get. Deceleration and negative acceleration are not the same thing. They're not interchangeable. Think of it this way. Deceleration is what's actually happening to the object. It's physically slowing down. This only happens when the acceleration is fighting against the velocity. They're pointing in opposite directions. Negative acceleration, that's just about the direction we picked on our number line. It just means the acceleration vector is pointing to the left or down or whatever we decided was negative. It could be speeding something up or slowing it down. Let's make this super concrete with a few car examples. Look at car A. It's moving to the right, so let's call that the positive direction. And it's speeding up. For that to happen, its acceleration has to be pushing it in the same direction, so the acceleration is also positive. Here's the rule. If the signs for velocity and acceleration match, you speed up. It's really that simple. All right, now check out car B. It's also moving to the right, so its velocity is still positive. But this time the driver hits the brakes. It's slowing down. So where does the acceleration have to be pointing? Well, it has to be pointing the other way, right? To the left, so it's negative. And because the acceleration is opposite to the velocity, this is what we call deceleration. Now, car C is where it gets really interesting, and this is the one that proves the point. This car is moving to the left, so its velocity is negative, but it's also slowing down. So if it's moving left and slowing down, the acceleration must be pushing against it, to the right. And what did we call the rightward direction? Positive. So get this, we have a positive acceleration, but the car is slowing down. See, it's all about the directions being opposite. And for our last one, car D. It's moving left, negative velocity, and it's speeding up, going faster and faster to the left. For that to happen, the acceleration must be pointing the same way, to the left. So the acceleration is also negative. Both are negative, so the signs match and the car speeds up. This is absolutely not deceleration. So you see the pattern, right? It all comes down to one thing. Do the signs match or not? Okay, I think we've got a good handle on that. So let's put this knowledge to the test with another real-world problem. This time, we're hopping on the subway. So I want you to picture this. You're standing on the platform, and a subway train is pulling into the station. It's going a pretty steady 30 kilometers per hour, and then the driver hits the brakes. It smoothly comes to a complete stop in 8.00 seconds.
Our job is to figure out what its average acceleration was during that time. Okay, this is your chance to be the physicist. Here's what we know. Initial velocity is 30 kilometers per hour. Final velocity is 0, because it stopped. And the time it took was 8 seconds. So I want you to actually pause right here, grab a pencil and paper, and try to solve it yourself. But I'll give you one little hint. Watch out for your units. All right, did you get it? Let's walk through the solution together. The very first thing we have to deal with, and this is a classic trap in physics problems, is the units. We've got kilometers per hour, but our time is in seconds. We can't mix those. So we have to convert 30 kilometers per hour into meters per second. When you do the math, that comes out to 8.33 meters per second. Okay, now we're ready. The change in velocity is final minus initial, so that's 0 minus 8.33, which gives us negative 8.33 meters per second. Last step, we just divide that by our 8 seconds, and we get our average acceleration, negative 1.04 meters per second squared. And that negative sign should make perfect sense. The train was moving forward, but it was slowing down, so its acceleration had to be in the opposite direction.
Phew. Okay, so we've covered a lot. Let's boil it all down to the absolute must-know takeaways. What's the stuff you really need to remember from all this? Let's do a quick recap.
First off, acceleration is just the rate of change of velocity. Simple as that. But remember, velocity is a vector. It's got speed and direction. So if you change your speed, or you change your direction, or you change both, you are accelerating. And here's the golden rule, the most important part. If the signs for acceleration and velocity are the same, the object speeds up. If the signs are opposite, the object slows down. And that specific act of slowing down, that's what we call deceleration.
And just to leave you with a little something to think about, a little brain teaser. Imagine a car turning a corner. The driver is super smooth and the speedometer stays locked at, say, 30 miles per hour the entire time. A perfectly constant speed. So my question for you is that car accelerating? Think about everything we just talked about, especially what makes velocity a vector.